Okay. Last time I told you about this surprising result that Humphrey Davy had discovered in 1814, that both diamond and pencil lead, graphite, are the same stuff, carbon. And I forget who said it, but somebody, was it Daniel guessed that what was going on is that there are two different forms of carbon, and it's the structure of the carbon atoms that's different in the two cases. See, the atomic theory opens up the possibility of explaining just this kind of strange thing, that you could have the exact same stuff, but in a completely different form. And because in the atomic theory, you have not only the stuff, but the arrangement, the structure of the stuff, the way the atoms are arranged with respect to one another. And that's exactly what's going on in diamond and graphite. Now, Humphrey Davy didn't know this, but later it was shown that in diamond, the carbon atoms are all hooked up to one another, basically, in a three-dimensional lattice. But in the graphite, they're only hooked to each other in two-dimensional planes. So there aren't bonds between the different carbon atoms in all three dimensions. And that's what causes this huge difference in the properties of the two substances. Now, chemists actually discovered a couple of other materials that exhibit the same sort of behavior, the same exact stuff, but exist in two different forms. And one of them, well, first of all, let me tell you the name of these things. They're called allotropes. Okay, so the first case I told you about was carbon, and the two forms, very different forms, are diamond and graphite. But another element that is an allotrope that exists in two quite different forms is phosphorus. Chemists found out that there were two materials that were both phosphorus. Only one of them was, they were different colors. One of them is white and the other one's red. And later, when they were able to do a structural analysis, what chemists found out was that the white form of phosphorus consists of 4 phosphorus atoms that are bound together. So that are bound together in groups of 4. And then there's just all these groups of 4. Okay, so this is what they called P4. Whereas the red form was all of the atoms were bound together. So it was a continuous, what they call a polymer. In other words, it was all the atoms hooked to all the adjacent atoms, on forever. Whereas here you had groups of 4. Let's just say all atoms hooked together. So I mean, this is somewhat like the diamond case, where in the diamond you had this continuous, three-dimensional lattice, and that's what you have here in the red form of phosphorus. In the graphite case, you have it's only in a two-dimensional plane that the carbon atoms are hooked together. And here, in the white form of phosphorus, it's they're hooked together in little pyramids, groups of 4. Okay, I'll tell you about one more well-known allotrope. You've probably all heard of the chemical ozone. Okay, do you know what element it is? It's oxygen. The only difference between ozone and the regular oxygen that's in the air is this is the normal oxygen that's in the air is O2, right? Because we talked about how oxygen is one of these diatomic molecules. But well, let me actually, to be consistent with what I did before, just write. Let's call that the normal form of oxygen. And then there's ozone, which is O3. So 3 oxygen atoms hooked together. And again, they have very different properties. Normal oxygen is, we breathe it all the time. It doesn't smell. Ozone has a smell to it. Anybody know? I don't know. I mean, I know it has a smell because ozone in Greek means smell, smelly. So that's why they named it that.
It's the smell in the air after a lightning storm.
Yeah, right. I mean, I know that it's created by lightning, or if you have like an electrical short or something, a spark. If you get a little smell of what the air smells like after that, you're smelling the ozone. Troy.
How do you get from oxygen to ozone?
How do they create ozone?
Yeah.
Actually, I'm not sure how they would create it commercially. I mean, I know you can create it in some small quantities just by a strong electrical spark, but there's probably a chemical synthesis. I've got my chemistry book here. I'll look it up for you and try to tell you this afternoon. Okay, so here's 3 cases where you have an element, the exact same stuff, but existing in 2 very, very different forms. And when these were first discovered, the atomic theory, was still controversial. Chemists hadn't, a lot of chemists hadn't accepted it yet. So, these were important pieces of evidence. You can see how the atomic theory gives you a way of explaining what is otherwise a very hard to understand result. If you don't have atoms and everything is, matter is just continuous, then it's just hard to see how you could possibly have the exact same stuff existing in 2 radically different forms. It would be like if you were making something in the kitchen. Let's say you make and I used to make when I was younger and trying to gain weight, I used to make chocolate shakes for myself, and I would put in a couple of eggs and some milk and some ice cream and some chocolate and a banana or something and churn it up in a blender. Okay? Well, what if you did that one time and you got, this chocolate banana shake, and then you did it exact same thing the next time, and you got a steak sandwich? That would be pretty weird. There wouldn't be any way of understanding that, right? Well, that's almost what this is like. It's like if you have a continuous theory of matter and you don't have atoms to work with, and you analyze two radically different things like diamond and graphite and find that they're the same stuff. That's this puts a continuum theory of matter in a lot of trouble, and it's good evidence for the atomic theory. Okay. Now, the next thing I want to tell you about, which is very similar to allotropes, but with chemical compounds. And the next thing that chemists discovered was something they called isomers, which is actually, again, they chose this word from the Greek. Greek meaning equal parts. And let me explain what these isomers are. Chemists discovered compounds that, when they did the analysis, broke down into the exact same elements in the same proportions, and yet they were very different compounds. Let me give you an example. I'm going to choose ethanol, which is a type of alcohol. It's the normal alcohol that exists in alcoholic drinks. Okay? So you can just think of that as what you know as alcohol. And there's another compound called methyl ether. Now, these two are radically different chemical compounds. The alcohol, for instance, has a boiling point of 78 degrees Celsius. Okay, water boils at 100 degrees Celsius. Room temperature on the Celsius scale, temperature scale, is about 20 degrees. Right? So, okay, now, methyl ether is a gas at room temperature. It boils at minus 24 degrees Celsius.
So you normally have to keep that extremely cold.
Yeah, if you want it in liquid form, you'd have to keep it down at minus 24. Now, the chemical properties of these two compounds are very, very different. For example, if you take a chunk of sodium metal and you throw it into the alcohol, you get a violent explosive reaction. Okay? Sodium. If you take a chunk of sodium and throw it in down, sodium reacts strongly with a lot of things. I mean, you can take a chunk of sodium and just throw it in water and it will explode. But throw it in methyl ether and it doesn't do anything. It just sits there. Okay, so the chemical properties of these two compounds are very, very different. You know, what they'll react with. So, and of course, I mean, they smell different. You know, the alcohol has a sort of pleasant smell to it, and I don't know what the ether smells like, but it doesn't have such a pleasant smell. But when chemists actually analyze these compounds to figure out what elements they were made of in what proportions, they found the exact same. They were made of the exact same stuff, even in the same proportions. That they were both are 2 parts carbon, 6 parts hydrogen, 1 part oxygen. Sure.
Write that as C2H6O.
Yeah, so you could write, I mean, the chemical formula that they came up with for both of these compounds was C2H6O. So what's going on here? I mean, 2 radically different chemical compounds. Any ideas? What could explain this? Troy.
Those the atoms are like just arranged differently in each molecule.
Yeah, they are. I'll go ahead and tell you. At this point, you know, when they first discovered this, they didn't know. I mean, it took them a little while to figure out exactly how the atoms were arranged. But I'll jump ahead and tell you. The alcohol has the 2 carbon atoms hooked together. And then one of the carbon atoms has the oxygen hooked to it. And then the hydrogens surround those carbon-oxygen atoms in the way I've drawn here. Now, so in this case, the oxygen atom is out here on the end. Now, any ideas on what the ether might look like? Daniel. Yeah, the oxygen is between the 2 carbons in the ether case. So you put the oxygen in the middle, and you have an arrangement with a carbon and 3 hydrogens on each side of that oxygen. Now, you can see, I mean, without knowing a lot more chemistry, you can't just look at these structures and figure out how the chemical is going to react. Chemists can. But you need familiarity with the subject before you can do that. But you can see that there's a potential here for maybe radically different chemical properties in these two cases, because here we have a completely symmetrical molecule in which the oxygen is buried in the center. Here you have an unsymmetrical case where the oxygen's out on the end. And so if you have a chemical that can, say, react with oxygen that you put in with this, well, I mean, it can get to the oxygen in this case. And it can't get to the oxygen in this case because the oxygen's in the middle. Okay. So, yeah, right. So the sodium, reacts strongly over here and doesn't react over here. But again, see the way the atomic, thinking in terms of atoms, opened up the possibility of explaining what would otherwise be an inexplicable result. You have the exact same stuff in the same proportions, and it has radically different chemical properties. But the atomic theory gives you a way of understanding that. So this was really the first isomers were discovered in the 1820s, and I think this is really strong evidence for the atomic theory. It's just hard to understand a result like this without the atomic theory. So you see the way scientists were able to, you're starting to see, hopefully, how scientists were able to figure out that all matter is made of atoms. Because, again, it's not by building some super duper microscope so that you can look at atoms. That's not the way they did it. The way they did it is in these indirect methods, where they're just working with, they're working with billions and trillions of atoms at a time here. They're not looking at a particular atom. But the fact that they can make discoveries like this that they can explain with the atomic theory and can't explain without it is driving them to accept this fundamental truth that all matter is made of atoms. Okay, now I'll just give you one more example of an isomer. It's actually one of the first isomers that was discovered in the 1820s. There's, let me see, cyanic and fulminic acid. And both of these, again, they have different chemical properties, but both analyzed into one atom of hydrogen, one atom of oxygen, one atom of carbon, and one atom of nitrogen. Okay, so they both analyzed into that. And again, it turned out to be a case where let me see, cyanic acid was they were hooked up in that order, and the fulminic acid the carbon and nitrogen were reversed. And that led to different chemical properties. So again, it's the same thing that we saw in the other case. Now, let's let me see. Let me wrap up one point about the work that the chemists are doing around this time and in the early decades of the 19th century. Before I tell you next one thing the physicists are doing that's closely related to the developments in chemistry. I mentioned that when chemists analyzed water, they found that by weight, if you had, say, 1 gram of hydrogen combining with oxygen, it would combine with how many grams of oxygen? I told you at one point. Daniel?
8.
Got it. Yeah. So 1 gram of hydrogen combines with 8 grams of oxygen. Now, what's the molecular formula for water? Yeah.
H2O.
Yeah, H2O. So there's 2 hydrogens and 1 oxygen, right? So what is the relative weight of oxygen and hydrogen? Yeah, it's 1 to 16. Now, this is exactly the kind of reasoning the chemists were doing now to figure out the relative weights of all the elements. So let me just, and they started one of the new terms that was being used by chemists in discussing these elements was the atomic weight of the element. And they were working out these weights based on all the reactions that they were doing. Now, so let me give you a list of some atomic weights that were worked out fairly early in the 19th century. So in the first column, I'll put the elements. And in the second column, I'll put the atomic weights. Now, hydrogen is the lightest element. So we're just, by convention, we're just going to call that 1. Because what we want is the relative weights of the elements. And all the other elements are going to be heavier. Now, chemists had been analyzing a lot of reactions with carbon. And they had investigated gases like methane that are combinations of hydrogen and carbon. And they had invested gases like Black's fixed air, that was carbon dioxide, right? It's a combination of carbon and oxygen. So they, by breaking those down and weighing the constituents, they could come up with the relative weight of carbon to hydrogen. Turns out to be 12. Nitrogen worked out to be 14. Oxygen, as we've already said, is 16. And let me just give you a few more. Sodium is 23.
What's sodium symbol?
Oh, it's not very intuitive. Na.
Is that Greek or Latin?
Yes, probably. I don't know. I don't know where the word sodium came from. Okay, aluminum is 27. Chlorine is 35. Copper, 64. Let me see. Well, I'm running out of room here. I wrote too big. So let me continue. You can continue the same column if you've got room on your paper. Let me see. Silver worked out to be 108. And let me see. Well, I'll just write one more. A real heavy one. Worked out to be 208 for lead. Yeah. Troy.
What are the symbols for silver, lead?
Oh, okay. Aluminum seems to make sense. I think that one's Al. Chlorine, Cl. Copper, Cu. Yeah, silver is Ag, and lead is Pb. Okay, so you can see these numbers vary quite a bit. I mean, lead being, every atom of lead is 208 times heavier than an atom of hydrogen. So it's, the gases that we're most familiar with, air is made up of nitrogen and oxygen. They're relatively light. But the metals, some of the metals are quite heavy. Now, I can't pass up this one point. It turns out, I've cheated in a couple of these cases because, I've rounded off. Turns out that chlorine isn't exactly 35, but it's a little more than that. So they don't come out exact whole numbers, some of them, but a lot of them come out very, very close to whole numbers. Carbon is almost exactly 12. Nitrogen almost exactly 14. Oxygen almost exactly 16. And same is true for a lot of these other numbers. Now, does that strike you as odd, or would you expect that? Does it tell you anything? If you think about it this way, when we discovered, for instance, when Dalton started this whole business with the atomic theory by showing that, his law of multiple proportions, that elements combine into compounds in these simple integer ratios of their weights. And he immediately concluded, it must be because they're made of atoms, because atoms can only combine, one atom or two atoms. So you're going to get these integer multiples of weight. Well, here we're seeing another integer multiple thing here, that for some reason a carbon atom is exactly 12 times as heavy as a hydrogen atom. An oxygen atom is exactly 16 times as heavy. Now, does that suggest anything? Well, I mean, is it possible that, for instance, one French chemist decided when he saw these whole numbers, his thought was, maybe all these other atoms are made up of hydrogen atoms. In effect, there are hydrogen atoms that are combined in some way that chemically can't be broken up. Because otherwise, why would, I mean, if they're completely independent, you see where I'm going here, at least the logical train? I mean, if they're completely independent, why would they come out exact integer multiples in weight? It suggests a connection between these atoms and the structure and the way that these heavier atoms are made, has to be related to this, fundamental unit, which is the hydrogen atom. Now, chemists got that idea very early, but it was a long time before they could really figure it out and do much with it. And of course, one of the things that confused them was the exceptions, because there are a few exceptions, chlorine being one. This isn't just 35. It's actually closer to 35 and a half, which obviously means there's something wrong with this idea that all the atoms are just made up of hydrogen atoms. And it would take scientists a long time to sort out this mystery. But that original idea that French chemist came up with very early in the 19th century, that maybe all these other atoms are made of hydrogen atoms, there is something to it. He was on the right track. And we'll get to that by the end of the course. I'll explain exactly the structure of these atoms and why it comes out this way. Okay. Now, it turns out that these atomic weight numbers would be extremely useful to scientists. And I'm going to show you a couple of ways that scientists use these numbers to come up with further discoveries now. And the first way was not even done by chemists. It was done by a couple of French physicists who were investigating heat. So let me see, we only have 5 minutes left, but I'll go ahead and get started on this next topic that I wanted to talk about. Okay. Well, before I tell you what these two French physicists did, let me introduce the topic by. I can't remember how much in the past I've told you about heat, so let me start back at the beginning. You tell me whether this sounds familiar to you. First, there's a distinction between heat and temperature. Does that sound familiar? I mean, the simplest way to see that there has to be a distinction between heat and temperature is imagine putting 2 pots of water on a fire to boil them. Okay, but one pot has 1 liter of water, and the other one has 2 liters. Okay, which is going to boil first? Daniel.
1 liter?
Yeah, obviously, right? I mean, you can heat up 1 liter a lot faster than you can heat up 2 liters, twice as fast, actually. So clearly, it takes more heat to raise the temperature of water if you have more water. Now, so just in that sense, we can make a clear distinction between heat versus temperature, right? That at a given temperature, I mean, to raise the temperature of, say, a bunch of water by a certain number of degrees, obviously the amount of heat that you need is directly dependent on the amount of water that you have. Now, the physicists actually defined a unit to capture this idea. They 1 calorie they defined as the heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Now, probably you're familiar with calories by the way people talk about food, right? The number of calories in an item of food, and that's just this exact idea. Only when they talk about it in the context of food, it's not the same unit that physicists use here. It's this unit multiplied by 1,000. In other words, it's basically the energy or heat required to raise the temperature of 1 kilogram of water by 1 degree. So there's that factor of 1,000 difference between the calories that they talk about in food and the calories that physicists talk about. Okay, so, well, our time's up this morning. I will continue with heat this afternoon.